Hola, buenos días. ¿Cómo están esta mañana? Eso, parece que aquí están mejor que ellos, ¿no? ¿O no? ¿Cómo están? Eso. Mira, the best school of Antofagasta, they're telling me here. ¿Es verdad eso o no? No. ¿Quién? A ver, ¿cuántos colegios tenemos aquí? ¿Cuántos colegios hay? A ver, nombre. San Esteban. Inglés alemán. Por ahí hay otro, ¿no? No alcanzo a escuchar el... Ebenezer. Ebenezer. Ya. Que acá se escuchan lejos. Ya. ¿Y de qué cursos vienen? Sixth grade. Segundo, tercero medio. Ya. Cuarto medio. So we have people from like 12 to 18 years, something like that is our audience. It's a very difficult audience. So, well, welcome. Primero voy a partir a few words in Spanish. Ojalá que me ayuden. No es fácil entrevistar a un premio Nobel, así que necesito ayuda, ¿ya? Participación, cuando quieran nos interrumpen. Si tienen alguna pregunta de cualquier tipo, científico o personal, tenemos que aprovechar esta instancia. Así que me interrumpen. Si quieren decir la pregunta en español o castellano, me lo dicen. I was just telling them to interrupt me if they want to participate. Okay, so we're going to start this activity. Now we're going to be talking in English. And as I was telling you, it's kind of intimidating to interview a Nobel Prize winner. So I need help, please. But I'm very lucky, because if you are not a specialist in the field, which probably none of us are, all the science around André Geim seems kind of surreal, no? It's very interesting because he studied very complex and difficult things. I think I'm going to turn this off.
Okay, yeah.
Yeah? Okay. For example, he talks about materials that are only 2 dimensions. Can you imagine that? It's like if one of you were only 2 dimensions, I could be able to see you in the front, but if I don't know, I just imagine it that way. He's going to explain it. But maybe I won't be able to see you if I'm looking in this edge.
Yeah.
So,
okay.
Welcome, Professor Geim. Thank you for being here in Antofagasta, and I hope we have a very interesting talk today.
Thank you for having me here. Buenos dias. I'm sorry, I do not speak Spanish. I speak 3 languages, but neither of them is Spanish. Yeah.
So, as I was telling our audience, this scientist talks about material with only 2 dimensions. He's been levitating water, frogs, and who knows what else. We're going to ask him. And at least theoretically, he's been working on how to understand the gecko, you know the geckos, kind of lizards. You know geckos? ¿Conoce los geckos? So, yeah, so I've heard these scientists have been working in how to make kind of gecko gloves. Do you imagine having gloves and socks that can make us move like geckos? I really like that part. But incredibly, all of these, what I'm talking about, it's really exact sciences and not Marvel fiction, no? And for that, he has won the Nobel Prize and the Ig Nobel Prize. So the first thing I would like to ask you is where were you when you have between 12 and 18 years old? And what were you motivated about? What were you thinking about at that time?
It's probably people in this audience, if you are better in certain subjects, for example, in exact sciences, your teachers, your parents encourage you to do even better there. If you are bad in singing, in drawings, in art, in literature, then probably you lose your interest. So initially I was good, probably due to my parents who were technical people. I was good in exact science, in mathematics, in physics. And so gradually I grew up and got all kind of Olympiads when I was at school, and then went to the best possible university to get my education in physics. So it's nothing special. Encouragement by teachers and encouragement by my parents.
And you were born where you were born?
I was born in Soviet Union. Now it's Russia on the Black Sea coast. It's the climate. Usually people think of Russia very cold, but I was born in the climate similar to Santiago.
And afterwards, you went to study abroad, no? To study abroad?
Yeah, after my university, which was in Moscow, I got a few years of independent research as a junior researcher in the Academy of Sciences in a research institute. But when the Soviet Union disappeared, I went to look for luck abroad, in Denmark, in UK, and my essentially 5 years of so-called postdoctoral studies, being kind of a researcher under some professor's supervision, and eventually I got my permanent position in the Netherlands, Holland, where I have become a faculty.
So, Dr. Geim, I would really like to talk with you about how do you, so what intrigues me is how do you kind of train your curiosity, your creativity? This activity is called a scientist is born or is trained, no? And so when you in your Nobel lecture, you mentioned that you did your PhD in an area in a subject that was not
extremely
really
boring.
He said it, extremely boring. That really no one was super interested in that. Actually, he mentioned in his Nobel lecture that he published 5 papers that were cited twice by the authors only.
Yeah, by my supervisor.
But then, if you continue reading, and I really recommend it, this is what professors that are awarded the Nobel Prize read when they win the Nobel Prize, and they are fascinating pieces of work. You know, it's super interesting to read. I recommend it. And then, after that, if you continue a few pages, then you realize that the same person has become a very creative scientist that invented kind of he had these Friday night experiments activities where they do good science, but also questions that sometimes you could see they are kind of playful, sometimes maybe even from outside you could say this is a silly question to ask, but very interesting science. So let us know kind of that process. How do you start to become a scientist, like less, I can imagine yourself in the first years like more aware of the restrictions and then maybe more open to new ideas. How do you train your curiosity?
It's in a sense it's very simple. We who work at the universities were professional scientists. We try to do something really narrow within area of expertise, but sometimes it's extremely boring, and if I would start explaining you what I'm normally doing in my working life, it's so narrow area of research that you would fall asleep in 5 minutes. So, and most people do that. We have to be professional to narrow up. But at the same time, we are humans. We also want to do something for our souls, something interesting. And I have developed this style, especially with PhD students who come there and they don't want actually to be bored. And I gave them a small projects and doing them together with them, which are for fun. Just let's try something which looks not very hard to do using the facilities which we have, but at the same time, might be it brings some fun or some kind of, we don't know the answers. Usually the questions are scientific. So let me give you an example of what we were doing, how it usually works. Let me put it this way. So I was working in Holland at that time, in the Netherlands, and the question was quite interesting, whether we can find some new phenomena which were not known before with simple water all around us if we put in very high magnetic fields. My advantage in this case was that we have reasonably high magnetic fields. They were around the world, but they're actually about 5 times stronger than you would get in the hospital. But apparently no one was silly enough to ask this question before. So once upon a time, I pour water inside this rather expensive equipment inside. As say, people use those magnets in many countries for many years, but somehow no one did this experiment before. And the result was remarkable. You see what you see, a tennis ball of water freely hanging in the space, like in gravity, like on the space station. There is air blowing through to make it move, otherwise it would be a static image. It's intentionally do that. So the reason behind this levitation is not anti-gravity, it's compensation of gravity by strong magnetic field. And I'm well educated, so I realized in 5 minutes, maybe 5 hours, that it's a simple, known for 100 years phenomena. But people assume that this phenomena is very feeble. And my colleagues next day didn't believe me that it happened, so I have to show them. The most surprise was that no one appreciated what's going on. And then my colleagues start coming with ideas, what else can be levitated, and so on. And we described the physics behind this. And then at the end, there was so much interest in this levitation, then I decided to make something appealing to everyone. So at the end, we make this picture of the frog and make with a TV station a small movie with a very small frog levitating there to say that everyone and everything around us is kind of magnetic. So if we put you inside magnetic field, you would also levitate, because we're all a little bit magnetic in this sense. And the biggest surprise, it's not the physics behind, which requires a lot of formulas, and we publish proper papers, but the point that people assume that it's extremely weak phenomena. It's not. Now this is coming from a simple question, going all the cycle through scientific research. Now this picture in dozens of textbooks, and I think it stimulates a young audience who sometimes send me this kind of fan mail. I'm 9 years old and I want to become a scientist. Okay, so that's really heartwarming to get this kind of lectures. So simple experiment with good physics behind, but at the same time it was a great fun to do this one. And it was not boring, as the main part of my research was.
Bravo.
Thank you, muchas gracias.
Any ideas if you want to like levitate somebody? Your professors maybe? No.
Levitate, fly away.
So what is super fun is that for this experiment, Professor Geim was awarded the Ig Nobel. Do you know the Nobel Prizes, don't you? Do you know the Nobel Prizes? ¿Conoces los Premio Nobel? Yes. Do you know the Ig Nobel? No. Okay. So there's a US, an American magazine called Annals of Improbable Research. Yeah? And invented this kind of satirical Nobel Prizes that are called the Ig Nobel. And are for research, what they say is that it's research that makes you first laugh and then think, you know. And so André Geim got awarded for the Ig Nobel in the year 2000, no? And then 10 years later, he won the Nobel Prize, the real one, not the satirical one. And I think it's the only scientist, well, it is the only scientist in the world that has had both awards, the Nobel and the Ig Nobel. So I think that's very interesting, no? And what is very, it's like in these Friday night experiments, not only he has been levitating frogs, but also you discover a bunch of other things. Particularly, you also started working in graphene, like around these Friday night experiments, no?
Yes. Let me move here.
Someone here knows what is graphene? El grafeno. ¿Saben lo que es el grafeno? No tienen por qué saberlo. ¿Sí? No. Sí, he knows. Do you want to tell me what is graphene? Come here.
Come here.
Come here, come here. No, está bien, dilo fuerte, dilo. What is graphene?
He escuchado del grafino, pero, o sea...
Okay, he has... okay. So now we will all learn what is graphene.
So it's again started, I never dealt with graphite or carbon in my career before. So it started with a simple question: how thin graphite can be made? You know what's graphite? It's in your pencils, a material which allows you to draw lines on the paper. And apparently people tried to make graphite very thin, but there was no possibility of doing this somehow. So we use seemingly ridiculous and seemingly naive approach. You know what atom is? It comes from a word atom in Greek, which means indivisible. And atom was kind of invented by philosophers 2,000 or 3,000 years ago, when one of the philosophers in Greece asked, what would we take a stone and divide it into two, and then another two, and then another two, and then continue until we come to a concept of atom, where you can't divide the matter into anything smaller than that one. So this kind of experiment we did in the lab. You take a sticky tape, Scotch tape, attach it to graphite, and what you see on this Scotch tape, pieces of graphite. Then you bend the Scotch tape and split it again, and then split it again, and then split it again, until you start seeing very small pieces of graphite. And you know, graphite is a metal. Metals are not transparent. But when you see a metal which is transparent, on this picture, light shines through the screen, and you see some pieces like this one, which are, I can't show it there, some pieces which are very transparent. It means, it means that, like here, it means that it's a very thin piece of graphite. And no one has done this before. You see how simple is this. And this was a new material, a single plane of graphite. And essentially what we have taken, we split graphite into those individual atomic planes. You probably know that crystal contains of rows of atoms and planes of atoms. So essentially, using this sticky tape, we extracted an individual atomic plane. That's now called grafeno or graphene in English. And that's how it looks like. You see, it's a single atom of carbon. It's a crystal. You can see it by naked eye. It absorbs a little bit of light. Actually, it's a lot for a single so thin material. And this was the foundation of a new type of materials, which are only one atom and one molecule thick. Those materials were presumed not to exist in our universe. They were very powerful theorems which forbid those materials to exist. So we overcome all those laws of nature by backdoor and found out that there are this kind of materials. No one suspected just 20 years ago that this whole bunch of materials would exist. And it's all started with a simple question.
So, and these new materials, you know, because you're talking in general, but then we know you started with graphene. Which other materials? Is like other family of metals that are as thick as graphene appeared afterwards?
Yeah, it's essentially the Nobel Prize acknowledged the paper in which we extracted this graphene, individual atomic planes, but this was not for extraction, it was for showing how wonderful properties of this material is. And when we studied this simple material, we find out that it shows a lot of different properties. For example, since we in Antofagasta, people know what copper is here. For example, it allows currents which are 1,000,000 times higher to go through this cross section of graphene than through copper. But the most what we learn from this material that it's very different from graphite. Usually when you take a part of something, this is similar to a big, the parent one. It turned out to be not true. All those materials turned to be very different from parent material. Graphene is completely different from graphite, which was a big surprise. And in our second research published half a year later, we have shown that graphene is not alone, that there are many similar materials which are just one atom thick. And that's a big thing which already 20 years on, and people continue investigating thousands of the lab around the world, 100,000 papers published every year about this kind of materials, about their properties and how different from parent materials they are and how wonderful they are.
So I think this list is very impressive, you know, it's like, so Dr. Geim have just described just this very, it's like a thin, the thinnest, it's like from your graphite pencil.
The thinnest material you can imagine.
It's the strongest ever, also the stiffest, is more, it has more conductivity, is completely impermeable. It's really amazing, you know. You wouldn't think that. It's like completely counterintuitive, no?
When we started, we thought that, okay, it's fun to extract so thin materials. Maybe it will bring us something small, something interesting, and it turned out to be a completely new universe, which we still continue. No one expected it. Even with benefit of hindsight, you can't imagine that it could happen, how it happened. So no one expected this one.
And that's why the world has recognized the work of Dr. Geim with the Nobel Prize. And so how has it advanced since then, since 2010? Does it has today concrete applications, or people are speculating on how to use it? Is it, how has the world been working on that in the last years?
You know, until 10 years ago, we worked Scotch tape, and it's called Scotch tape technique. It's the most used technique around the world. Everyone who is dealing in this area of research called two-dimensional materials, they use this technique still because it gives the highest quality materials. But at the same time, applied physicists, applied engineers wanted to use this material, and until 10 years ago, we didn't know how to produce this material. Now we can make it in tons as a small flakes, and if we need, we can make square kilometers of those. So only 10 years ago, people start looking what can be done in those materials. So my colleagues came with hundreds, thousands of different possibilities. What can you do with this material? Sometimes it's science fictional materials like lifts to the moon, or many others which will never happen. But occasionally, out of those dreams of graphene, some of those dreams have become a reality. And these days, you find graphene already in many products, in batteries, in mobile phones, on the street lighting, for example, in solar cells. It's not a revolutionary applications. It's adding graphene to other materials to improve their properties. For example, in Antofagasta, here, because copper is very important, I know that my colleagues here work with engineers who work on electrolysis, try to improve the process of extraction of copper out of the copper ore, make it more efficient, and they use graphene for this reason as an additive to electrodes which you use in an extraction. So it went to 1,000 different applications, and it's already makes an impact. It's both good and disappointing at the same time. Good because there are so many different applications, but I'm personally a little bit disappointed because we have these wonderful properties. We have hundreds and even thousands of different materials similar to graphene, and at the moment it's just additives to other materials. There is no kind of revolutionary product yet which say, wow, this is only due to graphene. So at the moment we just improve properties of the existing materials, but we hope all that it will change in some not so distant future.
So have you, like, I know you're in the science part, not in the application, but have you thought in a, like in that wow, as you just mentioned, like in which way would this probably be have an application that would revolutionize some area, or what's the crazy idea people have proposed about the use of graphene?
I'm not industrialist, as I said before, and I'm also not futurist who can predict future. I don't have a crystal ball. I have several applications in mind. For example, one of the cousins of graphene is semiconducting material, and there is a lot of interest to use these semiconducting materials instead of silicon. Silicon is in every mobile phone, in all our gadgets, but it's bulky, like non-transparent applications. But those one-dimensional materials can beat silicon when it becomes on this very small kind of material. So people working intensively to have a new materials instead of silicon. There is, let me show you something else. I'll give you an example. There are so many applications. I'll give you an example of this one. You know what the Philosopher's Stone is?
Harry Potter says there. ¿Saben lo que es la piedra filosofal?
No, but
Yeah.
this is not from Harry Potter. It's different.
Oh.
Okay. So the Philosopher's Stone was kind of an imaginary material thought in the Middle Ages. When you use this material, it turns, for example, lead into gold or some other material into whatever you want. Usually people spend their lives for centuries looking for something which can transfer rubbish into gold. That was the original non-Harry Potter's Philosopher's Stone. So, and in graphene works in a sense as the real Philosopher's Stones. In our case, rubbish is electronic waste. It's what people throw away when your computer or your mobile phone is broken. This all it becomes rubbish, and it's very difficult to recycle it, but it contains a lot of different materials, including gold, which you would like to extract. And it's very hard. But what we did, it's only a year ago we published this research. We dissolved this in aqua regia. It's a mixture of two acids. And at the end, we get some liquid which we pour through the collection of graphene flakes. It filters this liquid. It's a real-time experiment, and what you see at the bottom, it's gold comes here. Everything else goes through, and only gold appears on graphene. You tried it with any other material, including graphite itself, you don't get it. But it's gold inside, and then it's very easily extracted by burning graphite into the gold. I don't know whether it will be used in future for extraction of gold from electron rubbish or not. It requires, viability studies, how it's economically, but you see it's kind of a magic which still we find with this material. Again, it's very different from graphite, its parent material, which doesn't work this way. So many possibilities are open for this one. And I can give you many other examples what in principle it's possible, but I think it just gives you an idea how unusual the material is.
Well, interesting. We learned about the real philosopher's stone. So I need to ask you about the gecko tape. I think it's one of the, it really blew my mind. Do you know geckos or lizards?
I'll show you this.
Have you ever asked why do they really are able to walk through the walls or even the ceiling? So Professor Geim studied also that.
So that was, again, Friday night experiment in a sense. I have never dealt with animals except for the frog before, and I'm not biologist, and these geckos, and you know that they climb walls, they can stick to the glass ceiling, and part of my colleagues' research was to figure out what the phenomena behind this is. It's toes of geckos, which you see on here. No, it doesn't show. On the right, covered with billions of very small hairs, and those hairs each sticks to the opposite surface with a very tiny force, 1 nanonewton. It's 1 billionth of a newton. And this is when you touch anything, take your hair and touch opposite surface, it would be the same nanonewton force. And this is called van der Waals force. It's like one atom's touch another atom, and then they try to stick together. No glue, nothing is there. Geckos learn how to use billions on those hairs at the same time, so 1 nanonewton multiplied billion times, it gives you 1 newton, which is, if you learn physics already, which you know enough to keep geckos on glass ceilings. So this is how it works in principle, and the idea, which is maybe not so trivial, but it was kind of, wow, if it's simple, it's so simple, why can't we use what we have in our facilities, done my routine work, which is taxpayers pay money for, in a kind of late experiments, a little bit using facilities which are already there for doing other things. Why we don't reproduce this forest of tiny hairs using plastic? And here on those pictures, you see a forest of artificial gecko hairs, and they stick to the surface. Was very expensive to produce a large amount of tape, but at least you see a demonstration that we can make gloves very small gloves. It was a start of a research area which is called dry adhesives. Adhesives which do not use any glue, which use on the same principle as Gecko use. And a few years later, about 10 years ago, I saw a real person hanging from the ceiling using this kind of scaled up version of this Gecko tape. Unfortunately, we don't have Gecko gloves yet, because the problem, somehow geckos, they manage to clean their hairs from dust. In our case, whatever we produce now, after a couple of attachments, this forest clamps and it stops working on the same principle. But it's a vibrant area of research. Many people try to make this true.
I think we really need to, with all my respect, you need to work further on that. We need the Gecko gloves and the Gecko socks, no? To climb the ceilings. A big applause for all of you, and especially for Professor Geim. Thank you very much for being here. Thank you, all of you, for this conversation.